Ball and socket joints are the next type of support that we want to consider in 3D R cross F analysis. So consider this pipe assembly here. It's got a distributed force of 800 newtons per meter, and it's supported by those two strings that are tied to the wall. So let's draw a 3D free body diagram that looks something like that. And I'll draw the forces on. There's a distributed force that looks like it's coming down. How big is that? It's 800 newtons per meter times 3 meters. So that looks like that is 2,400 newtons coming down, kind of right there. And the strings, they're coming from the middle here, so I'll just draw one like that. I don't have to be super accurate there. Now let's draw the supports. The supports, again, of a ball and socket joint are only in the X, Y, and Z direction. Sorry, there are only forces in the X, Y, and Z direction. There are no moments because it spins freely about each axis. So I'm going to draw a force in the X direction, a force in the Y, and a reaction in the Z. And this looks like it is point A, so I'll call that AX, AY, and AZ. Okay, from there I think we can start doing some work. First of all, let's define the forces. Force dB. Here is our 3D Cartesian look at that, force dB, and here's the unit vector, and then we can solve that out. Force dC. Here's the unit vector for that. Again, we don't know the magnitude of those forces. All we do know is the direction at this time. And then we need some R vectors. So let's look at the R vectors. We're going to sum moments about point A, and the one R vector for the for each of these forces, well, again, we could have an R vector here for that one, an R vector here, or we could go right there for both of these forces, and that looks pretty good. That'd be one in the I direction, one in the J direction. So that was considered R1. For the distributed force, it's coming straight down in the middle, and you can see that the distributed force goes down through the x-axis right there. And so this is actually the line of action, or this is the line of action of the force, and could be a good point for the R vector. Just draw it to right there. So that'd be 1, 1.5, plus another 1.5, which would be 4 in the I direction. All right, with that, let's just sum the moments. The moment, again, no moment reactions at A. It's just the sum of the moments about A is equal to the sum of the R cross F's, because there's no moment reactions, and you can see how I did that. I've got for the distributed, or sorry, this is for force dB. There's the IJK and the unit vector. Again, this is the way I do it, is put the unit vector of the force and then the magnitude on the outside, and that works pretty well. You could put this into each one of these pieces. It feels a little clunky to do that, so I'm going to put the magnitude on the outside. We'll just basically factor it out of the equation. And this is force dC. Here's the unit vector, and there's the R vector. And then for the distributed force, I do know that the distributed force is negative 2400 K. I talked about the R vector being that. Multiply all those out, I get all of those things. Now we just sum the I's, J's, and K's. So here are the I's. I guess I got that all in there. That looks pretty good. The I's are this times that minus this times that, or this plus a negative that, and so that's how we get there. It's probably easy to see too that because it's symmetric, they're going to be equal to each other in magnitude, just opposite in direction. The J's, FDB times negative 1.14, FDC times negative 1.14, but then I got a 9600 in the J direction, and then in the K direction, what's my 9600? I guess I got that from, this is from the dot product, is be the J. All right. In the K direction, what have I got? Let's see, go back up here and see in the K direction, I got that for the K and that one in the K. Put those equal together to get to 0. And through this, I can see that FDB and FDC are equal to each other. That gives me, that comes from those two equations. And then we just sum the forces in the x, y, and z, and we can see that we have AX and AY and AZ. And that's really what we're looking for, is the forces in those directions. Those are the reaction forces. So again, I hope that that's clear. It's pretty straightforward. The only difficulty really is just doing the cross products, identifying the good R vectors, and then drawing the proper free body diagram is also essential, obviously, to know what forces we're actually trying to solve for.